Chapter 4, Vacuum Flashing. The discussion so far about distillation curves and distilling columns have treated the shape of the curves and temperatures close to 900 degrees Fahrenheit somewhat vaguely, but on purpose. There is a phenomenon that happens at these temperatures called cracking. Refiners use cracking extensively, but in controlled ways. In the distillation process, all the uncontrolled symptoms of cracking can occur. To avoid them, refiners developed vacuum flashing. Subject: the cracking phenomenon. Suppose a technician were going to develop a crude distillation curve in the laboratory. Technicians do that all the time to prepare essays for use by refiners to help assess the suitability of crudes. The technician would heat the crude oil, note and record the temperature, capture the vapor and condense or liquefy it, and record and accumulate the volumes of liquids. If the technician permitted the temperature of the crude to rise to about 900 degrees Fahrenheit, a sudden change in the shape of the distillation curve would take place. As the temperature went from 900 to 1,000 degrees Fahrenheit, the cumulative volume would would exceed 100%, and crude would still be boiling in the pot. This might exaggerate what anyone can easily observe with the naked eye, but it makes the point. As the complicated hydrocarbon molecules, they have not yet vaporized at 900 degrees Fahrenheit, are heated to higher temperatures, the energy transferred from the heat is enough to cause the molecules to crack into two or more smaller molecules. For example, in figure 4.1, a molecule of carbon 16, hydrogen 34 may crack into three pieces: carbon 8, hydrogen 18, carbon 6, hydrogen 12, and carbon 2, hydrogen 4. A fuller discussion of the chemical reaction of cracking will be covered in the chapter on cat cracking. If you recall the discussion on boiling points, it starts to become apparent why the shape of the distillation curve behaves so strangely at this point. The smaller molecules boil at much lower temperature than the larger ones. As cracking creates them, they leap out of the crude oil. That tells only half the story. Why does more volume get created so that the distillation curve exceeds 100%? In simple terms, the smaller molecules take up more room than the larger ones. Again, recall the discussion on hydrocarbon properties and specific gravities. The compound C16H34 weighs 7.2 pounds per gallon, and C8H18C6H12 and C2H4 weigh 5.9, 5.6, and 3.1 respectively. Take a gallon of C16H34 and suppose you could crack it completely into these three compounds. It never happens that way. Combinations of different compounds turn up too. The chemistry of it says that there would be 50% C6H18, 30% C6H12, and 12% C2H4. The percentages are by weight, not by volume. Figure 4.2. To make the calculation easy, start with 7.2 pounds of C6H34 and calculate the change as follows. Note the calculations on the top of page 41. Cracking is a lucrative process only when it is controlled. The distilling unit is not designed to control it, so refiners avoid it by not raising the temperatures in the distilling process. The heaviest cut point on the distilling column is around 750 degrees Fahrenheit. There are, nonetheless, lots of hydrocarbons that need to be separated from the straight-run residue, and the technique used is vacuum flashing. Subject: effects of low pressure. Suppose Suppose you own a chain of restaurants that specialize in serving stuffed baked potatoes, one in Houston, Texas, and one in Denver, Colorado. Do you know that baking potatoes in Denver takes 20 minutes longer than in Houston? I found that out the hard way when I went skiing in the Rocky Mountains and cooked my own supper at night. The reason is that at the higher altitude in Denver, the atmospheric pressure is lower. When people say the air in the mountains is thinner, they really mean that there is less air per cubic inch. Since the pressure is lower, water will not boil at a lower temperature. Even though you have the oven set at 375 degrees Fahrenheit, the boiling moisture will keep the potato at a lower temperature of 205 degrees Fahrenheit in Denver, not the 212 degrees Fahrenheit in Houston. Thus, the potato doesn't ever get as hot in Denver as it does in Houston, and it takes longer to cook. All this illustrates the simple relationship between pressure and temperature. The process of heating lets the molecules absorb enough energy to escape from the liquid form to the gaseous form. The rate at which they escape depends on the rate at which the heat is delivered. How high you turn the burner, and the pressure of the air above them. The lower the pressure, the less energy has to be transmitted, and the lower the temperature at which the vapor will start forming in the liquid, in other words, boil. The point is, the lower the pressure, the lower the boiling temperature. Subject: vacuum flashing. Apply the pressure/boiling relationship to the crude oil cracking problem. The straight run residue will crack if the temperature goes too high, but straight run residue needs to be separated into more cuts. The solution is to do the distillation at reduced pressure. In the vacuum flasher shown in figure 4.3, straight run residue from the distilling unit, while it is still hot, is pumped into the flasher. The flasher is a large diameter vessel, too squat to be called a column, but that's more or less what it is. The straight run residue leaves the pump and heads down the line into the flasher, where the pressure has been lowered well below atmospheric pressure. At that low pressure, the lighter portions of the straight run residue will vaporize, but at that temperature, no cracking will take place. Various gadgets inside the flasher facilitate separating and capturing the offtake steam. As the mixed steam of vapor and liquid enter the flasher, almost all the liquid falls to the bottom. Some of the liquid forms droplets, not quite gaseous, but carried along with the vaporized part of the straight run residue. They start to rise with the vapor. To capture these droplets and to disperse the vapor evenly throughout the flasher, the vapor/droplet mixture encounters a note distributor, a thick mesh screen or a tray of loose metal rings several inches thick. The distributor catches the droplets, which drip down to the bottom. Further up the flasher are two trays that operate the same as those in the distilling column. There will probably also be a reboiler, though it's not shown in the figure. Reflux, serving the same purpose as it does in the distilling column, is in the same form of a liquid spray from the top of the vessel, using some of the cooled streams drawn off one of the trays. The note vacuum pump at the top of the vessel maintains the low pressure in the vessel and continuously draws off any vapors that have not condensed, and usually consist of small amounts of water and hydrocarbons. Some vacuum flashers use a device called a steam eductor to maintain the low pressure. The two streams drawn off the upper part of the flasher, note light flashed distillate, and note heavy flash distillate, together are called note flasher tops. The two streams are often kept segregated. Refiners found through chemical analysis that the heavier part of the flasher tops contain most of the contaminants that poison catalysts in processing units further downstream. By keeping the streams segregated, they can heat the heavy flash distillate and remove most of the bad actors. Meanwhile, at the bottom of the flashers, the liquid drains very tight. Some flashers have apparatus for one last pass at removing the good stuff. They pump some superheated steam up through a pipe as the liquid comes down, releasing some lighter hydrocarbons that may have been entrained in the liquid. Because the superheated steam is at temperatures well above cracking temperatures, the liquid coming out of the bottom, the note flasher bottom, is quenched with some cooling liquid before the cracking has a chance to take place. The flasher bottoms have several destinations. Feed to an asphalt plant, a thermal cracker, a coker, or as a blending component for residual fuel. The reason to run a flasher is to make the flasher tops to heat to a capped crack. Review. Flashing is the equivalent of distilling a straight run residue at a cut point in the neighborhood of 1,000 to 1,100 degrees Fahrenheit. Crude oil distillation curves always show the temperature-volume relationship as if the theoretical distillation took place, i.e., they assume the vacuum flasher is part of the distillation unit.